Dear colleague, so nice to see you. Nice to see. I hope you are happy to see me again on YouTube here. So, what about this week? What about today? We are going to conclude our lessons about the R language as used in medical statistics. And now we want to move from the concept of the linear model to a wider concept which encompasses many different phenomena, many random variables. We used to study the linear model because it was very useful if the research we are doing can be modeled by some numbers, some real numbers, which comes from some measure, they possess some unity of measure, and these real numbers distributes according a Gaussian, a normal distribution. Okay, and this is typical, for instance, with the Fleischer data set. You remember when we studied the weight of the people, of students, boys and girls, assuming that they are, in a sense, distributed as a bell shape. Okay, we have the technique on the linear model, but think about think about a very common situation in medical statistics, and for instance, think about the coronavirus, and we perform a test, and we detect whether virus is present or not. This is binomial distribution. Okay, it's very typical. And as we want to investigate whether this binomial random response is related to other possible predictors and covariates, we cannot exploit the linear model because 0 1 on off, yes, no, dead, alive, positive, negative, and so yin and yang, and what you want uh, is not Gaussian, and so it has not sense to perform a linear model, and and we are going to show this. Okay, all what shall we consider? Do you remember? Do you remember the question of the ovarian cancer? 10 years ago, in 2008, 2009, an important group from the United States of America published the so-called Roma index of risk. Roma, ROMA, do you remember? The risk of ovarian malignancy, index. And they provide a paper in which they study a huge sample of women, uh, and they detect the role, the possible role of two important biomarkers. One was well known and let's say an ancient biomarker. It's called the CA125. Okay, and the other was pretty new in a sense, and it seems more reliable. And the human epididymospore, let's call it HE4. So CA and HE were two possible candidates, okay, to detect the ovarian malignancy risk of cancer in women. Okay, after a couple of years, an important relevant papers appeared from a group research from India and Australia. It was 2013. Kondalsamy and Obermeyer published this differentiating stage 1, blah 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 blah, adding more predictors besides this HE4 and CA 125, they added the other biomarker CEA. Never mind here about the biochemical characters, features of these molecules, and also the patient age. But we went to read the paper and have a look here, the table. They distinguish between, let's say, young and older, let's say, women, in a sense, pre-menopausal status and post-menopausal status. And they considered HECA 125 and CEA and also the age. But please have a look on the table of the result. The premenopausal, the postmenopausal, and the overall. Please have a look. Have a look to the p-values, the famous p-values. Okay. You see that the biomarker CEA, the cancer antigen, neither in premenopausal nor in postmenopausal and nor in the combined solution, joining together in a sense young and old women, okay? Neither in all three cases the third biomarker appears to be significant in a statistical sense, despite the fact that the title of the paper claimed that this can be use a combination, can be also, you can find also in the results, can improve the ability of prediction. So this was the, 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 the sparkling idea of our colleague Shadi Najaf, and we started to investigate about the possible role to clarify this position. So Shadi considered her Roma data set, and in a while we will upload it into R and also into our commander, as you prefer. And she started to consider 210 patients from our local here at Trieste Catinara University Hospital, and also Burlo hospital here in Trieste, and yes, she started to study, to model this this data set, okay, and of course, we are not able to perform a linear model, neither to test regression, ANOVA, and COVA, no, because the response is the histology, which can be benign or malignant, okay, 1, 0, okay. It is not possible if we perform the command linear model, symmetry model, the R provide an answer, the negative answer, an error message, okay. We are not able to compute this. Of course, because binomial, I say, is not Gaussian. So we need a trick. The trick was well established in the late, let's say, 80s, more or less. And the structure of the statistical model is called GLM, generalized linear model. And in GLM, we can achieve the result to model not only Gaussian, but also binomial, Poisson, do you remember? To count as we count. And also many other random variables, more even interesting, okay? The problem is that everything is not really straightforward. It's a little difficult to think about the concept of the residuals. what is the deviance? How can I compute it? Where are the minimum square, the sum of the squares in regression? Well, okay, there are some tricks and some details. Many calculations are performed not in an exact manner by an iterative and approximate, okay, solution, but the algorithm exploited are very efficient. This is the typical Newton-Raphson way to compute the root of a function. So everything converge normally in very quickly in 4, 5, 6 steps, and so the computation really are in a sense simple for a modern computer. And from the theoretical point of view, we have a concept, okay, because the linear model, the generalized linear model is in a sense a set of one, two, three tools. Okay, so we have the first tool is so-called the linear predictor. Also, people calls predictive index. This is nothing more than the line, the straight line, the y equals a plus bx. The output commonly we know from the linear model. This is the linear predictor, okay, first object. The last object, the third object, is the binomial family of random variables, of course, because the histology here is on off. Cancer, yes, cancer, no, okay, benign, malignant. And the third ingredient of the generalized linear model is the so-called link function, a function which links the predictor, the linear predictor, to the output, which is the binomial, okay? So something converting from a number, a numeric number, into an, for instance, on-off answer. There are, okay, many generalized linear model possess many different link function. We are considering today the binomial distribution, and so the link function is the so-called logic transform. Which is the logic transform? But it is nothing that the logarithm, the natural logarithm of the ratio of the two probability, of the probability of success and the probability of the complementary event. So P over 1 minus P. And if you look at this function, you see, okay, its domain is from 0 to 1, like in the probability we require, and the output is all along the real line. So inverting this link function, inverting the logic, we obtain the typical sigmoidal function. There are many possibilities, but the simplest is the ratio of the exponential over 1 plus exponential. And this is a good trick because the function moves from minus infinity to plus infinity, so all the real number, converting into the image, converting into 0, 1, which is the space of the probability. Okay, so having a linear predictor, having a real number, we can obtain a probability from 0 to 1. This is the correct link function to understand, to correctly interpret the model. Okay, so for example, following the book, we will compute for one person of a certain age, a certain condition, and certain biomarkers value. We are able to compute with our commander, the probability of illness, the probability of cancer. Okay, So this, in a sense, is the big plot, okay, the framework, and of course we are able to exploit uh, all the tricks, all the tools we have, in particular the archaic information criterion to detect the, the minimal adequate model, and we will do it, we will check it, and we will see that Shadi Najaf in her Roma dataset find some little difference between the paper provided by the author, by Moore et al. Okay, and yes, this is this, and so we are going. I am going to sit down to show you everything with a computer. Okay, and then for the last homework, I will provide you a sort of test of quiz. Okay, so okay, now I go to the console, to the R console. Okay, in a while. Ready? We go to the ictpmmp.weebly.com website, and we scroll down. We move to, for instance, to look to the slide. So take the codes and data, the same button, and we join the sixth lesson. And here you can find the Roma dataset. Okay, you can simply download it and put it on the desk. I already did it. Here I have the CSV dataset. So we are ready to start. Let's start with R. Okay, a new session, clear, and file new document in order to save the commands. Provide a name, also file, save as, let's call it lesson6. Good, save. So do you remember we are required to read what a CSV or CSV file. So it is a function. Where is located this CSV? Well, we will find it browsing file dot choose, open and close, with the header equals true. This is the syntax, and we provide a name to this data set. We call that easily Roma, as usual. So Roma equal read CSV file choose. We attach the Roma, okay, and if we want to look everything, we say Roma, but you remember it's quite messy, 210 patients, so we can only give a look, for instance, to the structure of the data set. Okay, 1, 2, 3, run. Here, sorry, run. Okay, let's go to the Roma CSV data set. Better to see it. Okay, here 210 patients and 7 columns. Okay, 6 columns are the covariate, the possible predictor, and 1 the goal. The goal is the histology. Okay, which can be luckily benign or unfortunately malignant. Okay, and this is the response. This is the primary investigation object of our data set. Okay, so we want to study histology. Okay, and if you remember, if you exploit the command tail, you obtain, which is quite useful to remember, the last 6 rows of the data set. if you want the last 11 rows, tail row my 11. Okay, what would you prefer? Just to have an impression and an idea of the data set, like having an Excel spreadsheet data. Okay, so we were wondering wrong. We were wondering if a linear model can be useful to study the histology. For instance, with respect to for instance, respect with the menopause status, if you want, or the age of the patient, of the biomarker, the possible biomarker. Okay, let's try to do it. No. We obtain a warning. Something doesn't work properly. Nevertheless, we obtain some result, but now this is, we do not want this. Okay, the problem if you ask for the summary of this linear model, the warning is more strict and say no, really, no. What we are talking about? What is the residual? We cannot compute this. Okay, and this is not a linear model, a regression line. Okay. Well, okay. So do you remember maybe in the Moore paper? Let me search here in my library. Moore, where is Moore 2000 and something? Comparison between maybe this or maybe this work. Perfect. This is the paper, the original paper, and they provide two indexes. The first one predictive index referred to the premenopause status, and one predictive index referred to the post-menopausal states. Okay, and you see they are related to the HE4 biomarker and also to the CA125 biomarker. So we have 1, 2, and the menopause. 3 possible predictor provided, suggested by Moore and the other colleagues. Okay, please note there is a misprint here. The predicted probability, which is the logit, well, not the logit, the inverse of the logit function. Okay, the sigmoid function. It is properly written exponential of something over 1 plus, not divided, plus exponential. There is here a misprint. Okay, so good. So remember, 1, 2, CA, HA, and menopause are the possible predictors suggested by Moore. Okay, so let's move back to here to R. We copy here. I copy simply all the variables and rearrange them. So this is the response, and we want to model according to the menopause plus the logarithm of the human epididymis 4 and plus this cancer antigen 12.5. This is okay. This is the relation provided by Moore. On the book I call it Moore relation equals to. Okay, this is the idea provided by the author. Okay, and which is the idea of the colleague Shadi in her research with a capital S, sorry, Shadi. And she decided to investigate about all the possible covariate, okay? Because you remember Obermeyer suggested a possible role of this antigen and a possible role for the age of the patient, which in a sense masked by the menopausal status, okay? And also maybe some other authors providing possible role with respect to this other biomarker. And so they Shadi consider all these, okay? So we copy all again, copy. I put it here, okay? This is the histology tilde, the first plus the second plus the third plus the fourth, fifth, and last possible covariate of the study, okay? And this is the maximal relation which we can consider. Well, of course, this is an plus. This is an additive model without interaction. Of course, interaction is possible, and we will check for it. But we start, in order not to make troubles and mess with the convergence of the Fisher scoring method, we start here testing, detecting only the plus relation, okay? So this is plus. We simply consider this maximal relation, and we applied to it the generalized linear model, okay? Oh, sorry, here inside. Of course, we have to specify, and you can look here below, very small character, the family of the link function we require. Okay, we are concerning with the binomial response, and so that the family of the random variable is the 1, 0, the binomial. Okay, if you put here the word Gaussian, the generalized linear model of the Gaussian families is nothing else but the linear model we studied until the previous week, okay? Or otherwise, and other different random variables, as said, you can consider here, but this is the case, our binomial, okay? So this is the first model we consider. For instance, I call it maximal model, okay? And have a look to the summary of it. Okay, the output, let's have a look, okay? Just run everything. Okay, we obtain some estimate, like in the linear model, some standard error, like in the linear model. We do not obtain a t-value here, the computation, the test statistic. The statistic is not the t-distribution of student gossip, but it is the Gaussian, the normal distribution. So this is the reason why you see z and the probability of z. But it is the same role, okay? You see some stars, very high significant role of this covariate, so they are predictors. Other not starred predictors, okay? This is the entropy, the archaic information criteria, okay? And you see, but it's not important, not relevant to us, and you see that the iterative computation, the Newton-Raphson method converges after 6 iterates. But never mind. Okay, we will discuss a little also about this measure, the null deviance, the residual deviance. Okay, we will discuss in a while. Okay. This is the maximal model. Some covariate are not significant, not useful. Okay, we drop that away. We can do it by hand. You remember, starting from the less relevant, or you remember the last afternoon we say goodbye, arrivederci, ci vediamo la prossima settimana, we see you next week. Fake. We are at home. And you remember the lazy approach by the step, the magical step function. So we ask to R to step, to consider, to reduce, according the archaic information criteria, the model, and provide us the less expensive, the minimal adequate model. Okay, the minimal adequate model. The histology depends from the logarithm of the HE4, the logarithm of the CA125, and also the menopause. Well, is it the same? Is it the same of Moore relation? This? Well, no, actually, because Moore considered really not this. This is maybe this. This is my fault. This is my fault. This is not the Moore. This is the Shady relation. The Shady. Sorry. There is a misprint in the book. I apologize. This is the Shady, and after the step of the maximal modem, this is what Shady found. Okay. Well, Moore, as properly indicated in the book, I say, let's go here. Sorry, in my small. Where is the book? Small. Have a look, please. Here in the 7.3. I'm checking. Okay. And the relation is purely additive. No, there is not interaction between the predictors. In the paper, they consider the possible interaction, okay, between the okay, they provide two different, okay, relation. One for the premenopausal status, one for the postmenopausal status. Shady tried to verify this, or also this, okay, many invisible issues, and we consider different archaic the information criteria, okay, but the Shady model here, the Shady relation, was the one with the less archaic information criteria. We try also to consider the curvature, okay, inserting, if you remember, the possibility to well, allow to let's say, not straight behavior, but curve, convex or concave behavior of the biomarkers, both the CA125 and both the HE4. Okay, but here again, no satisfaction. The Shady relation was the optimal, the minimal adequate model. Okay, well, again, just a small command here. Let me show you here. So this is the Shady relation. This is the minimal adequate model. I put it here. Okay, this is the shady. This is the minimal adequate model. Summary minimal adequate model. Okay, good. Well, we have here some relevant question. Have a look here. Dispersion parameter for binomial family taken to be 1. What does it mean? What is this dispersion parameter? Okay, well, well, there is a trick here. The Gaussian distribution allow you to select for the centrality, for the mean, and also to select a possible dispersion, sigma, the standard deviation, okay, the variance, okay. Well, this is not actually possible in the binomial distribution, because when you, in a sense, when you choose how many trials you do, how many experiments, how many women you consider, 210, okay, and as you fix the prevalence of the pathology, the probability of the illness, okay, well, the mean and the variance are fixed. You cannot choose them, okay, and sorry, maybe this is a misprint. And p and variance is equal n times p times 1 minus p. Okay, this is a misprint. Okay, sorry, apologize. Let's check here. Wikipedia, mean variance binomial distribution. Here, I suspect that here, okay, this is written correctly. The variance is the number of the patient, 210, times the probability of success, which is an ugly success, the probability of the cancer, okay, times, again, 1 minus p. Q is the complementary of p. Sorry, there is a misprint again in the book. Sorry. Okay. And so let's go back. When you move from the normal distribution to the binomial distribution, in a sense, you are not free to choose the mean and the variance. Okay, they are in a sense fixed by the dimension of your sample and the prevalence of the pathology. So the important thing is, for technical reason, is not to have the phenomenon of the overdispersion. Okay, what is the overdispersion? Is the number of the residual deviance may be less than the degrees of freedom. Have a look. This 100 must be, in a sense, less than this 200. Okay, if you perform an analysis and you find here a residual deviance number which is greater than these, well, this is bad news, and you have to act on this dispersion parameter. Okay, how to do it? Well, simple, consult the help, the GLM help, and have a look here. Instead of using the family binomial, let's go here. You ask to the computer, to R, to compute for you the number of the parameter, the dispersion parameter. Okay, and instead typing family equals binomial, you type family equals quasi-binomial, okay, and automatically you obtain the correct dispersion parameter. The drawback is that in that case you are not able to compute the archaic information criterion by theoretical reasons, okay? Well, luckily this is not the case, okay? So we were able to find with the step function the minimal adequate model, okay? Now, okay, suppose let's interpret correctly this model, okay? Let's go back. For instance, better here, sorry, down, okay. So again, let's make it simple. This is the minimal model, the shadow relation, okay? We have an intercept, I put it here, okay, plus a possible number for the menopausal status, okay, plus a coefficient for the logarithm of HE plus the coefficient of the logarithm of C8125, okay? Well, let's do the example provided in the book. Suppose we consider a patient which has, for instance, 200 here, 2.96 of this biomarker. Okay, so we multiply this by the biomarker 3.96, okay, and suppose that such a person has 4.03 of this other biomarker times 4.03, okay, and suppose also that she is in the postmenopausal status, okay. We are referring correctly to the last person, you remember here. So I invoke here again tail lemma. Okay, we are talking about this woman, okay. Unfortunately, she was a malignant case, okay. She was in postmenopausal status, so we are required to add this coefficient. She was 63, but in the Shady relation, the age does not matter, so we do not consider, okay. She has this 0.71 for the log CEA, but no matter. 167 for this other biomarker, no matter, okay. 403 for the CA125, 403 multiplied for this coefficient, okay, and lastly 396 for this other biomarker, 396 for this other biomarker, okay. So computing this number minus 142 more or less, this is the so-called predictive index, okay. But this is not a probability. Okay. This is the log odds ratio. Well, never mind. We can compute the probability to have a malignancy just computing the exponential of this number. Okay. Or if you want to be more clear, okay, just this over 1 plus the exponential of the same number. And so a person having this and this biomarker being in the post-menopausal condition has a 19% according to the model of Shadi to be a malignant case. Okay, so good. This is everything about the R. Okay, good. So now our commander. Let's move to our commander. So our library our commander. Okay, let's open. Okay, we are ready. Well, do you remember data? Import data from text file or using the commas as field separator. Okay, and on the desk I go there. Something. Okay, Roma, open. Okay, here Roma. Here the data set has two. Okay, rows and 7 columns, 210. Sorry. View data set. Here all the patients. Good. Okay. We are ready. And okay, do you remember the paper? The Moore maintains that and collaborators maintains that the predictive index varies according to the premenopausal or the postmenopausal. You see, the coefficients are different. Okay, what does it mean? Look also the 2 points here, this symbol. What does it mean? It means that the menopausal status is a covariate which interacts with the other. There is an interaction. So in the model, Moore consider not the plus sign, but the cross sign. Okay, it's very simple to do it. All this with our commander. So let's do it. So this is statistics. Fit models, generalized linear model. Click here. Good. So we have to select the response. Okay. Well, the response, of course, the histology, and it is a factor. Good. Double click. This is tilde plus, and these are the predictors, the covariate. Okay. So they suggest that the menopause must interact, so not plus, cross, must interact with the human epididymis 4 and plus the menopausal status must interact, cross, with the mucin CA125. Okay, this is actually the model provided here. Okay, so Shadi Najaf performed this calculation, but you see, she does not observe the significance of these two. You see the double points here. Double points, the interaction. The interaction is not significant. So the Moore paper provide also different numbers. Okay, the intercept -12, -8 here, -10, and -10, -5, which is -15 in our computation, -15 here and -10. Okay, so 1.5 here in the premenopausal, 1.5, 2.3, okay, 0.5, 0.06 here, very different. Okay, and at the post, so on the post it is 1, 5 plus 1, 4 is 2.9, 2.9, 2.9, 1, 1 and 0. And so last this, okay, and so this 0, 5 plus 0, 2, which is 0, 7, 0, 8. Okay, 0, 7, 0, 8. Here we agree. Okay, so some figures agree, some are different, also quite different. Well, okay. So we were a bit puzzled about this. Okay. So you see, exploiting our commander, everything is really easy. Okay, good.